In this video, I would like to explain the concept of Anova Test in more depth. Analysis of variance, or ANOVA, is an inferential model used to test the equality of three or more population means. We are going to examine this process using the following example. Welds used to join metal parts are made by heating a powdered material called flux. In a study conducted by G. Fredrickson at the Colorado School of Mines, 4 welding fluxes with different chemical compositions were prepared. The purpose of the study was to determine whether the welds made from the fluxes would have different degrees of hardness. 5 welds using each flux were made, and the hardness of each was measured in Brinell units. The higher the number, the harder the weld. The data are presented in the following table. We have 4 fluxes, A, B, C, D. Each one has a sample of size 5. Flux A has the following hardnesses: 250, 264, 256, 260, 239, with sample mean of 253.8 and sample standard deviation S of 9.7570. Flux B has a sample of 263, 254, 267, 265, 267, sample mean of 263.2, sample standard deviation of 5.4037. Flux C has a sample of 257, 279, 269, 273, 277, the sample mean of 271.0, and the standard deviation S of 8.7178. And finally, Flux D has the sample of 253, 258, 262, 264, 273, with the mean of 262.0 and the sample standard deviation S of 7.4498. Each of the 4 samples may be thought of as coming from a different population. Below are the dot plots for the sample hardnesses using the 4 fluxes. Each sample mean is marked with an X. As you can see, the 4 samples have slight skewness, in some cases slightly greater skewness, but nothing extraordinary, nothing too unusual. This experiment involves an outcome variable. An outcome variable is the hardness, and an explanatory variable, which is the flux type. The explanatory variable is qualitative and is called a factor. The outcome variable is called the response variable. The different values of the factor, in this example, the different fluxes, are called treatments. Because there is only one factor, flux type, this is called a one-way experiment. The table above is called one-way table, and the method of determining whether the population means differ is called one-way ANOVA. There are a few assumptions that we need to meet before we can perform this test. First, there must be k simple random samples, 1 from each of k populations, or a randomized experiment with k treatments. Second part, the populations must be approximately normal. Finally, the populations must have the same variance sigma squared. Balanced versus unbalanced design. When the sample sizes are all the same, the data are said to have a balanced design. A balanced design is much less sensitive to violations of the assumptions of the equality of variance than an unbalanced one. Because moderate departures from this assumption can be difficult to detect, it is best to use a balanced design whenever possible, so that undetected violations of the assumption of equal variances will not seriously compromise the validity of the results. With a balanced design, the effect of unequal variances is generally not great. With an unbalanced design, the effect of unequal variances can be very substantial and can cause our results to be unreliable. The more unbalanced the design, the greater the effect of unequal variances is. When the design is unbalanced, we can check the assumption of equal population variances by computing the following quotient. Dividing the largest sample standard deviation by the smallest sample standard deviation. If the result is less than 2, we conclude that the assumption of equal population variances is satisfied. Of course, if this quotient produces a number that is greater than 2, then the assumption of equal population variances is violated. If we return to our example, and for convenience I copied the same table to make it available here, we can check the assumption for the one-way ANOVA, the assumption of equal population variances, by taking the highest standard deviation of 9.7570 and dividing it by the smallest standard deviation of 5.4037. The quotient results in 1.806, which is less than 2, and therefore we assume that variances are equal, and using the plots that we saw on the previous page, we also are assuming that there are no violations of normality because none of those dot plots show a significant extreme skew or say outliers. We continue going through this example and are getting close to identifying how ANOVA hypothesis test is processed. In our example, therefore, we consider comparing mean hardnesses of the fluxes. The assumptions are satisfied and we're ready to set our hypothesis statements. It will be pretty standard to say for the null hypothesis that the means are equal. In our case, there were 4 fluxes, therefore I'm saying there are 4 means that are equal. Alternative statement will say 2 or more means are different. Before we dive into the hypothesis process, let's identify important notation. K represents the number of populations sampled. Mu with a subscript identifying each population, of course identifies means for each population. X bar identifies means, and the subscript just tells you which sample mean we are talking about at the moment. Sample mean of first sample, of second sample, third sample, all the way to the kth sample. S represents sample standard deviations. A lowercase n represents sample sizes. Uppercase N represents the total number of data entries from all samples combined. And X double bar is the grand mean, which means the average of all items in all samples combined. The sample means x bar sub 1, x bar sub 2, x bar sub 3, and x bar sub 4 are spread out around the sample grand mean x double bar. One-way ANOVA provides a way to measure this spread. If the sample means are highly spread out in comparison to the x double bar, then it is likely that the treatment means are different and we will reject the null hypothesis. The spread of the sample means around the sample grand mean is measured by a quantity called the treatment sum of squares, or in other words, it's a variation between the samples. And this variation between samples, abbreviated as SSTR, is computed using the following formula. First, we find the difference between each individual sample mean and the grand mean. Then we square that difference and multiply this square by the sample size of this particular sample. First sample. We repeat this process for every sample. Again, look at the next one. Take second sample mean, subtract with grand mean, square this difference, and then multiply by the second sample size. When we complete all of these computations and add them together, we get this SSTR, the treatment sum of squares. To determine whether SSTR is large enough to reject null hypothesis, we compare it to another sum of squares called the error sum of squares. That number measures the variation within each individual sample. SSE measures the spread of the individual sample points around their respective sample means. The spread is measured by combining the sample variances. SSE depends only on the sample standard deviations, is influenced only by the population standard deviation sigma, and is given by the following expression. SSE is equal to sample size of the first sample minus 1. In other words, this is degree of freedom for the first sample, multiplied by the first sample's sample standard deviation squared, which really means sample variance. Repeat this process for every sample. Again, degrees of freedom for the second sample, n sub 2 minus 1, multiplied by sample variance of the second sample. Add these products for every sample and you get your SSE. The sum of squares, SSTR and SSE, have different degrees of freedom. SSTR has k minus 1 degrees of freedom because it involves the deviations of k sample means. SSE, or error, sum of squares, has uppercase n minus k degrees of freedom. Why? Because it involves degrees of freedom of sample variances combined together. When I add all of these degrees of freedom, I end up having the total of all elements in every sample, because n sub 1 plus n sub 2 plus n sub 3 all the way down to n sub k, if I add them together, that's uppercase n. But in each of those I had to subtract 1. It means I subtracted 1 k times. That's where this minus k shows up. When a sum of squares is divided by its degree of freedom, the quantity obtained is called the mean square. The treatment mean square is denoted by MSTR, and the error mean square is denoted by MSE. Again, to get MSTR, take the treatment sum of squares and divide by its degree of freedom, k minus 1. To get the MSE, take the error sum of squares and divide by its corresponding degree of freedom, uppercase n minus k. MSE is the estimate of sigma squared, which is the variance of each of the populations. It measures how spread out the samples are around their own means. MSTR measures how spread out the sample means are around the grand mean x double bar. This spread is affected by variance, population variance, and also by how spread out the population means are. If the null hypothesis is true, and all populations have the same mean, then both MSTR and MSE are estimates of population variance sigma squared. When the population means differ, MSTR tends to be larger than the population variance sigma squared, and thus larger than MSE. We use these two quantities to compute a test statistic for testing our null hypothesis, which states that the means are same for all the populations. The quotient of MSTR and MSE is giving us the F statistic needed for the Anova test. And this quantity describes a relationship between the variation between the samples versus variation within the samples. When null hypothesis is true, this ratio is close to 1 because these two quantities are about the same. When null hypothesis is false, F tends to be greater than 1 because the numerator quantity will be higher significantly in comparison to the denominator's quantity. This takes us to a summary of how we perform the Anova test using the critical value method. First, we state the hypothesis, and the statements will be very standard. Null hypothesis states that the means are same, and alternative hypothesis states that 2 or more means must be different. Make sure to check the assumptions before you run the test. Next, identify the level of significance alpha, which is typically given to us. We need to compute SSTR and SSE, and then by dividing each of these two quantities by their corresponding degrees of freedom, we will compute MSTR and MSE. Once we know MSTR and MSE, we use the idea presented above to get the F statistic. Then we need to find the critical value using the numeric solver function of TI-84 calculator with k-1 and n-k degrees of freedom. If test statistic F happens to be greater than or equal to critical value, we reject the null hypothesis and state the conclusion using the context of the story. I would like to demonstrate how to follow through this process using the example we have worked with so far. Again, for convenience, the table is again presented on this page. I'm starting by stating the hypothesis. The null statement says means are same. There are 4 of them. Alternative says 2 or more means must be different. Assumptions we already checked on the previous pages. Alpha, we're going to choose it at 5%, which is a very typical choice. The next step is to compute SSTR and SSE. To do that, we need to use the formulas I presented earlier. One of the formulas uses the grand mean x double bar. To find it, I need to find the average of the averages. So I'm taking sample means for those quantities and find the average of those. X double bar comes out to be 262.5. Now I will compute sum of squares for treatment. And again, following the formula, I multiply the sample size into the squared difference between the sample mean 1 minus the grand mean. I repeat this for every sample, and there are 4 of them, and add these results together, which yields 743.4. Then I compute, using the next formula, the error sum of squares, and the error sum of squares says to multiply the degree of freedom for each sample, which is 5, because there are 5 elements in each sample, 5 minus 1, that gives me a 4, multiplied into variance of each sample. Please notice that my table gives me standard deviation, so I need to square each of these quantities to get variance for each sample. Once I find these products for each of the 4 samples, I add these results to get 1023.6. Our next step is to use SSTR and SSE we just found to compute the mean square for treatment and mean square for error. So MSTR is equal to the quotient of SSTR divided with its degree of freedom, k-1. In our case, it is 743.4 divided by 4 minus 1. This results in 247.8. Similarly, MSE is equal to SSE divided by uppercase n minus k. In our case, it is 1023.6 divided by 20, because there are 20 combined number of elements in all samples together, minus 4, which is the number of samples. And that gives me 63.975. I am finally ready to compute the F statistic, which is the quotient of the 2 quantities I found in step 5. F is equal to MSTR divided by MSE, or 247.8 divided by 63.975. This results in 3.87, and that is our test statistic. Next step is to find the critical value corresponding to the 5% significance level we've chosen for ourselves. What is F sub 0.05? I am using the numeric solver function to solve the equation where I say there is 95% of area between 0 and some unknown point, which I don't know yet, with 3 numerators degree of freedom and 16 denominators degree of freedom. These are the 2 quantities that come from these 2 denominators, okay? And that yields this unknown upper limit of this interval to be 3.24, at which I place right here on my diagram. So I have a diagram of the F distribution with 5% of area in my rejection region, and the point that separates 5% from 95% happens to be 3.24. My test statistic is 3.87, which is greater than the critical value, which means it is located to the right of the critical value of 3.24. And as a result, it means that my test statistic lands in the rejection region. For this reason, I reject the null hypothesis, and I'm stating that at 5% significance level, we have enough evidence to conclude that the mean hardnesses are not the same for all fluxes. The following outline describes how to perform one-way ANOVA hypothesis test using the p-value method on TI-84. This method is very useful when you have raw data given to you. As usual, we start by stating the hypothesis, which is a standard statement. Null hypothesis says means are same, alternative says two or more means must be different. Decide on significance level, enter values into lists, and use a test called ANOVA, apply to the lists where you stored your data, and this test is located under Stat Tests menu, and it will perform all the computations that we've done manually in the previous example. This test will take care of that all by itself. All you need to do is fill out the table that looks like this. This is called ANOVA table. You need to identify for factor and error the degrees of freedom, the sum of squares, and the mean squares, and of course the F statistic. And for degrees of freedom and sum of squares, you also need to compute the totals using the numbers above. Once this table is filled out using the information that your calculator will produce for you, you also will see on the calculator the p-value, which you will compare to alpha, and if p-value is less than or equal to alpha, you will reject the null hypothesis and state the conclusion based on the context of your story. Let's take a look at our last example, where we are going to see how to use TI-84 to perform the Anova test. Manufacturers of golf balls seem to always claim that their ball goes farthest. 20 golf pros are randomly selected to test 5 brands with 4 golf pros per brand. Here are the results of each drive in yards. 5 brands are represented by 5 columns. Brand 1 has the following data: 286, 276, 281, and 274 yards. Brand 2, 279, 277, 284, and 288 yards. Brand 3, 270, 262, 277, 280 yards. Brand 4, 284, 271, 269, and 275 yards. Finally, fifth brand, 281, 293, 276, and 292 yards. Do the data provide sufficient evidence to conclude that a difference in mean driving distances exists? Use alpha of 500th. First, I state the hypothesis. The null hypothesis says that the means 1 through 5 are equal. Alternative hypothesis says 2 or more means are different. Second step is stating alpha of 5%. Third step is to run the Anova test. To do this, first of all, we need to enter these 5 sets of data into 5 lists in our calculator. Once that is done, we're going to run the Anova test. I already entered the data into the lists prior to recording this, so my data is already there. Now, I press Stat, scroll to the right to Tests, and scroll up to choose the very last test available called Anova. Press Enter. Now you need to tell which lists you would like to use for this test. I am going to list them one by one with comma separating the 5 lists. Once I'm done entering all the lists where my data are stored, close parentheses and press Enter. Voila, your test results are here. Please notice that you're given F statistic, p-value, then all the values related to factor, which you're going to input into your table on the left-hand side of the screen, and then again a group of numbers representing the error. These are the numbers we need to enter into our second row of the table. Let's write down those numbers. Degrees of freedom for factors 4, sum of squares is 458.5, mean of squares is 114.625. For error, degrees of freedom is 15, sum of squares is 695.25, mean of squares is 46.35. The totals are found by adding 4 and 15 to get 19, and 458.5 added with 695.25 gives me 1153.75. Don't forget to write down the F value into your table, and of course write down what the P value is that the calculator produced, and in this case it was 89 thousandths. Now that our table is complete and we know our p-value, we can make a decision. Because 89 thousandths is greater than 500th, we do not reject null hypothesis, and we conclude that there is not enough evidence that there is a difference between mean driving distances. At least there is not enough evidence at this level of alpha of 5%. If alpha was chosen for us to be 10%, we would reject null hypothesis because 89 thousandths would be less than or equal to the 10/100th. But because we were given alpha of 5%, we must keep our null hypothesis.